Hello everyone, once again Irodov problem. The Irodov problems are must if you want to rank high in IIT JEE Advanced, and also once you have completed the other solutions you should give it a try, Irodov one try. So today we will take up the problems related to man boat problem, river boat problem, or swim and river and swimmer problem, in which river flows with a velocity and the boat or the man tries to cross it. So the basics are very simple. You just need to apply it at the position. The one thing that you need to keep in mind, that whenever we say the velocity of a boat with respect to the river, that means this velocity in a still water. It is something like that. A train is moving, and if I say, let's say train is moving like this, it's this wide train and I am inside the train moving like this, and I say that my velocity is with respect to the train. So anyone inside the train will observe whatever the speed which you are traveling, that will be same whether the train is moving or the train is stationary. But someone outside the train will watch you with a different velocity and direction. So this is something you need to keep in mind, because that was something I was confused about, and even though I know all the things, I had a hard time solving the problems long back. So let's do problem number 1.7. I will explain it to you, and then there are two swimmers leave point A on one bank of the river to reach point B lying across the other bank. I will draw the diagram. This is point A, this is point B, and one of them crosses the river along the straight line AB, while the other swims at right angles to the stream and walks to the distance that he has been carried away by the stream to get the point B. So let's talk about the first one. But the first one is, somehow he is able to go straight across the B. And to do that, because the river is flowing on the right side like this with some velocity, he has to walk a little at an angle like this, because then the river will push him a little on this side, and when both of them balance, he reaches exactly at the opposite point. The other person, he just thinks that I am going straight, but because of this river flow, he is carried away to this point, somewhere along this point like this, and then he walks back to the point B. What we need to find was, what was the velocity u of his walking if both the swimmers reached the destination simultaneously. The stream velocity is given 2 km per hour. I will directly write this velocity, 2 km per hour. And the velocity of each swimmer with respect to water is 2.5 km per hour. So let's take the first one. How does the first one go? The first one swimmer, what he does is, he tries to swim along in this direction at an angle of theta, and his velocity is 2.5 km per hour. And to be able to swim right across it, how does he do that? This velocity has two components. One component along this direction and the other component along the perpendicular direction. So the perpendicular direction will be 2.5 sine theta, and this velocity will be 2.5 cos theta. So the river tries to take him along this direction, while this horizontal component, his velocity, is trying to take him in this direction. If the river velocity is more than the horizontal component of this velocity, the net velocity in horizontal side is on this side, and he will be drifted towards this side. If the horizontal component 2.5 cos theta is greater than this river velocity, he will be drifted on this side. In order that he reaches directly across it, the condition is 2.5 cos theta, this velocity component, horizontal component of his velocity should be equal to 2, or cos, you can write it 5 by 2. So cos theta will be equal to 5 by 2, 2 to 2, 4 by 5. And therefore we can get sin theta as 3 by 5. Now, with the velocity 2.5 sin theta, let's say this distance is d, then he crosses this river with this vertical velocity, and the time taken in crossing this river will be given by this vertical distance divided by this vertical component of this velocity. The horizontal component of the velocity is not used in the vertical direction. This velocity has nothing to do with what he moves in this direction. The time will be equal to this distance d divided by 2.5 sin theta. We can write it as d, 2.5 is 5 by 2, and sin theta is 3 by 5. So this becomes 2d by 3. So that's the first one. This is the time this person takes in reaching the B. Now let's talk about the second person. The second person, I will do away with the first person. The second person, he thinks that he is moving in this direction with a velocity of 2.5 kilometer per second. But because of this velocity, river velocity, he is drifted in this direction. And what is the time it takes to reach from A to B? This time let's call it T1. Then T1 will be equal to this distance divided by his velocity in this direction. The river velocity does nothing. It does not deviate it, does not do it. This velocity has no component in this direction. Therefore, the river velocity has no role in taking him, either reducing it or increasing the velocity of the person in this direction. So the time taken will be this distance divided by this velocity, or d divided by 2.5. Now with this, what happens now, what we need to find out is what is the time it takes to walk. So to do that, we need to find this distance, which you call as x. And what is that? He is moving in this horizontal direction with a velocity 2 km per hour. So this distance x will be nothing but the component of the net component of the velocity along this direction, 2 multiplied by the time. This velocity in this direction, the velocity of the swimmer has no effect, and therefore only this velocity multiplied by the time will give you the distance. And this time is nothing but this t1, or 2 into d divided by 2.5. Now, what is the time he takes to reach from this point to this point? This time will be, let's call it t2. That will be equal to this distance, 2 into d divided by 2.5 divided by the velocity u with which he is proceeding. Now what is our condition? This time t, 2d by 3 must be equal to this time t1. I can write it d by 5 by 2 plus this one. This I can write 4 by 5 d upon u. Cancel out d. We get 4 by 5 u. This thing is equal to 2 by 3 minus 2 by 5. Or we can write it as 2 into 5 minus 3. 2 by 3 into 5. 5 cancels. We get u is equal to, and 4 cancels. we get u is equal to 3 kilometer per second. The basic concept here is keep the vertical velocity and this horizontal velocity separate, and then your life will be easier. That was question number 1.7. I hope you like the solution, and let's now move on to question number 1.8. In 1.8, two boats A and B move away from a buoy anchored at the middle of a river along the mutually perpendicular directions. We have a river, and in the center of this river, we have two mutually perpendicular directions, A and B. The boat A moves along the river. Boat A is moving along the river in the buoy, and this boat B moves across the river. Having moved off an equal distance from the buoy, the boats return. Find the ratio of the motion of the boats, ratio of the times of the motions of the boat, tau A divided by tau B. So this moves a certain distance d, and then it returns back, and that time is tau A. This one goes here, moves back, and that time is tau. They are called tau B, and B need to find out the ratios of these two times. The velocity of the boat with respect to water is neta equal to 1.2 times greater than the stream velocity. So let us say the stream velocity is v, then the motor velocity is going to be neta times of v. So for the first one, this is the d distance it's moving. When it's moving in the forward direction, he moves with a faster velocity. The boat's velocity and the river velocity, both of them help him sail. The time taken, that will be less, that will be the distance d divided by the total velocity. V plus neta v, we can write v into neta plus 1. This is the time he takes from going from this point to a distance t. And then when he comes back, he has to move against the river velocity. So the net velocity effective for the boat will be neta v minus v. And then the time taken will be this distance d divided by this effective velocity will be v into neta minus 1. Neta v minus v, I am directly writing neta minus 1 into v. That is the tau A. The time taken by this boat A in going and coming back. The situation of B is a little different. He has to move along this direction, and in order to be able to do that, he will move a little in this direction, making let's say an angle theta. He is moving with his own velocity is neta v in still water. Now this velocity is v. He can move in this direction only when, as you saw in the last problem, if you have not seen, you can see the 1.7 solution. This neta v, the horizontal component of this velocity, must balance this stream velocity. That means neta v for boat B, we must have neta v cos theta must be equal to velocity. If this velocity v is greater than this component neta v cos theta, then this will overpower it and it will start drifting in this direction from the center. If neta v cos theta is more than v, then the boat will drift in this direction. And only when these two velocities are equal, that the vertical component of this velocity nv cos theta is the only velocity nv sin theta will be effective, and it will sail him in this direction. So from here, if it moves a distance d here, then this time taken here will be given by let's call it T1 is equal to this distance d divided by this velocity nv neta v sine theta. The horizontal component cancel each other, and even if they were there, they will have no role in the vertical directions. So that is my T1. From here we can write cos theta is equal to 1 upon neta. So sine theta will be equal to neta v square root of 1 minus 1 upon neta square. You can also simplify it a little bit by writing it as neta cancels, v square root of neta square minus 1. So once he reaches this point B, somewhere B, here, let's call it X, he starts to return back. And in the return direction, the river velocity is in this direction. So he must try to sail somewhere in this direction, making an angle theta, his velocity being neta v. And I will let you do it as an exercise. This, from the point of view of reaching exactly opposite, this direction or this direction is symmetrical, which means that the time taken T2 in returning will be same as T1. I can write T2 is equal to d upon v square root of neta square minus 1. This implies tau b will be T1 plus T2 will be twice of this thing, 2d divided by v into square root of neta square minus 1. So the ratio will be, so tau a was, the ratio will be this velocity divided by this velocity. Let's simplify this tau a. Tau a is equal to d multiplied by neta square minus 1, neta plus 1, neta minus 1, and neta plus 1, that will be 2 neta. Now tau a divided by tau b will be equal to 2 cancels, d cancels, so we get neta divided by neta square minus 1 multiplied by square root of neta square minus 1. This becomes 1 upon square root of neta divided by neta square minus 1. This is our answer. If you want, you can substitute the value of neta as 1.2 to get the final answer. They have tried to combine more than one thing in a problem, typical of Irodov's problem. And now we will move to the third problem, again a boat problem. But the concept wise, they are not as hard, they are simple if you understand them. 1.9, the 1.9, we have a boat moves relative to water with a velocity which is n is equal to 2 times less than the river flow velocity. The river is, let's say, moving with a velocity. This is river. It's flowing with a velocity, let's say v naught. Now, it rarely happens that you are moving with a velocity even less than the flow, but sometimes the river is flowing really very great speed. So the person who's trying to cross it has a velocity half of this, v naught by 2. So I should show it so that it looks realistic. I will show it longer and I will show it smaller, v naught by 2. Half of v naught, something like this. Okay, now he is trying to cross it. At what angle the stream direction must the boat move to minimize drifting? What is drifting? If I am able to reach directly here, I have no drift. I am not to the left, I am not to the right. If I go to the left of it, I have a drift. If I go to the right, I have a drift. This, it suggests that he is not able to reach directly opposite to this, which means he has a drift. Let us take a look if we can reach directly opposite to this. As you have seen, if you are not seeing the answer to 1.7 and 1.8, what causes the drift not to occur? If we do not want any drift, then we look at the horizontal component. This is the river and this is the horizontal component of this person, theta. Now, this is V0 by 2. This component will be even less than V0 by 2. That means this component will be even less than half of this drift velocity. So, no matter what he does, he is going to be drifted to the right of this river somewhere here. And you may be thinking that, let us do one thing. Why not give it the full whole velocity like this? Let's move in this direction. V by 2 here. The problem with this thinking is that he will never be able to reach because he will always be moving in this direction. There will be no component that will take him in the opposite corner. So somewhere along this line theta, he will be like moving in this direction net, but he will at some point of time, he will reach. He will have a drift, but he will reach there. The question is, how does he move in order that that drift is minimized? At what angle theta to the stream direction must the boat move to minimize drifting? Theta to the stream direction, I am taking this theta, then I can do calculation, reduce it from 180 degree to find theta. So this is V0 by 2, this component is V0 by 2 cos theta, and this one is V0 by 2 into sin theta. Unless the river has a t, then the time taken to cross will be given by t is equal to this distance d divided by the vertical component V0 by 2 sin theta. I can write it as 2d divided by V0 sin theta. Now, in this direction, horizontal direction, the net velocity is V0 minus V0 by 2 cos theta. Therefore, this drift x will be given by this net horizontal velocity, which is V0 minus V0 by 2 cos theta multiplied by the time, and this time is going to be the same as this time. In the time he reaches vertically here to here, you can think of in the time he takes from vertical drift is equal, vertical distance covered is equal to the horizontal drift. So this we can write is as V0 minus V0 by 2 cos theta multiplied by this time, this 2d divided by V0 sin theta. I can write it as V0 cancels out, 2 minus cos theta divided by sin theta into d. This 2 cancels here, V0 cancel here, and then we have 2 minus cos theta and this sin theta. In order for this distance x to be optimal, maximum or minimum, we must have dx upon d theta equal to 0, which means sin square theta sin theta, differential of minus cos theta is sin theta minus 2 minus cos theta, and differential of sin theta is cos theta. This must be equal to 0, which means sin square theta, I will convert everything into cos theta. 1 minus cos square theta minus 2 cos theta plus cos square theta is equal to 0. This cancels. We have 1 minus 2 cos theta is equal to 0. That means cos theta is equal to 1 by 2. And this happens when theta is equal to 60 degree. So theta is equal to 60 degree. We can say that the angle with the stream, this angle is going to be 120 degree. You can see that there is an optimal angle at which his drift is minimized. I hope with these three problems you should be able to pretty much do any river and boat problem.